So, let us get started. I will continue CUDA programming discussions. So, what we did so far, I mean I just showed you how to run simple programs, right. In fact, we took two arrays, added C equal to A plus B, right, that is what I did, and before that I did for two floats or two real number, integer, I think two integers. So, these are I put down quite a few references. So, this is a book by NVIDIA itself. Well, I mean now people have moved out, some of them are were in NVIDIA before. This edition 4th is a 4th edition book, and other books are also good, but this is one of the first books. Okay, I mean you can have a look. I think this book also has a lot of details. This one is okay, I should not okay, anyway, it is an interesting book, slightly lengthy discussions, it could have been briefer, but yeah, you can have a look. And NVIDIA has lot of information. NVIDIA developers website, you can see docs has quite a bit of well, lot of discussions. Okay, actually it is also convenient to go to the Google and search, and you get lot of information without going to the book, but book also has their merits. Okay, now let us get back. So, we need to understand grids, blocks and threads. So, I think I did tell you in the earlier lecture that threads are put together in block, right. So, you can tie them up and make a block of threads, and then lot of blocks together makes a grid. Okay. So, that is how they are organized. So, in this picture you can see that we have blocks, actually this well, the color thing has not come out well. So, 4 of them together, 4 threads make a block, 4 threads make a block. So, 0, 1, 2, 3, then another 4 thread will make a block. So, that is how it continues. Okay. So, the original slide has 4 blocks of 4 threads each. So, there are 16 threads total. In fact, yeah. So, it has advantage which I will tell you right now. So, block is combination of threads, okay, thread block, and grid is combination of grids, blocks. Grid is combination of blocks. So, the syntax is actually, well, I think dim grid, dimension grid. So, next slide I am going to give the syntax of exactly how to write. It could be, right now I am showing for 1 dimension, but it could be 2D and 3D as well. So, your block could be 3 dimensional. So, I need 3 indices, no, for x, y, z. So, we will come to it in a minute. Well, 3D is required for 3 dimensional arrays, is convenient, not required, but is convenient. So, right now dimension of the grid is so this is another thing. Dim grid, it does not mean that grid, there are many grids. Dim grid means how many blocks in the grid. So, how many blocks in the grid? There is only one grid here, and it has 4 blocks, and dim block means threads in the block. So, this you please keep in mind. Dim block does not mean the block dimension, well, block dimension, but thread in the block, that is what it means. It does not mean many blocks. So, how do I, so we saw this before, how do I start a kernel for GPU? This is a function which will run on GPU, this is called kernel function. Full form is kernel function, I made a short form. So, it requires 2 arguments, dimension of the grid which will give the number of blocks, and dimension of block, dim block, which is number of threads. Okay, and there are reasons why it is segregated, I mean are organized this way, and arguments, we can put arguments which will be arrays or some variables. So, we seen this before, I believe it was add, either I had number of blocks 1 and ABC. So, ABC was the array, or I could do it with 1 block and n threads. There are 2 examples I gave in the last class, 3 arrows, sorry, 2 not 2 arrows, 3 arrows. Okay. Now, advantage of threads, why should we have organization like this? So, it turns out threads, well, irrespective whether you make them in a organize them in blocks or not organize them in blocks, they all of them do parallel operations. So, every thread is running on a core and there are many cores. GPU, the advantage is it has 5000 cores, okay, and it can run 5000 threads, but you can generate many threads because they are one after the other, they come like a really like army, that is in very coherent way and they do lot of operations. So, we create more than 5000 threads, okay, and they will be doing work very fast. So, these are parallel operations, all cores are busy and just doing one by one. Single instruction multiple data, SIMD, right, that is this is what you should remember, SIMD, unlike CPU, which is multiple instruction multiple data. So, like soldiers in a grid. So, that example is quite apt. So, use many threads as possible. So, you should really generate lot of threads for your simulation of let us say 1000 cube data. You should have million threads. Do not worry about this, there is no million core, what will I do? It will manage it. So, 1000 cube simulation should have billion threads, 10 cube, 10 cube, 10 cube. You put that many threads, you organize it that way, okay. It will sequence it, that is not your problem. I will tell you how many blocks and how many threads are allowed right now in the present NVIDIA machine. So, large image, every pixel you generate a thread. So, as I said 3D grid, 2D grid you generate this like this, but right now for your project do not try this, this will not work on I mean this will just take too long, and so just try for 100 by 100 2D first. So, threads can be okay. The one advantage is okay, one let me just make this remark which I am going to do it bit later as well. So, these are blocks B0, B1, B2, B3 and there are threads within. It turns out the threads within are synchronized, that means they are working together, okay, and also they can communicate via shared memory. There is something called shared memory which I am going to come to that, shared memory, and the shared memory can be used for doing operations which involves all the threads like sum. How will I do a sum of numbers? The threads are independent, I do not have a loop. So, each thread can do its work, but does not know how to communicate with others. So, then we use shared memory. Okay. So, threads are synchronized and there is some cooperation among threads within a block. So, that is why blocks are important, and if I want to communicate, make communication via two blocks, then it has to be by global memory. So, this I am going to come to it again, but this is an important point to keep in mind. Okay. So, let us look at 3D. So, block is, as I said, is combination of threads. This is a repetition. So, DIM3. So, DIM3 is a object, and so this is a syntax. So, dim grid 2. So, this is x direction, y direction and z direction, abstract direction. Okay. I mean there is no x, y, z in the computer. We are organizing our grid as 2 by 2 by 1, and the example is here. So, this grid 1 has did I say one grid? So, you can have multiple grids. Okay. So, that was a mistake. So, we have two grids here. So, grid 1 4 blocks which is organized as 2 by 2. 1 means there is no the index will be 0. So, there is no depth in the in the z direction. So, x and y take values 0 0, 0 1, 1 0 and 1 1. So, 4 blocks. So, if you are doing 2D simulation, it is a good idea to think like 2D grid, right. So, I have a big array, I can divide in blocks first, then within blocks there will be threads. So, indexing is natural ij, so you can use that index, though the data will be stored in 1D, basically data is stored as 1D, but you can visualize them as 2D for your convenience. And dim grid gives you blocks in a grid. Okay, this is what I said, these blocks in a grid, and there can be more than one grid. Now, we can define dim block which will give me threads in a block. So, it is 4 2 2. So, you can see that the indices are here. So, this is a block, this block has been zoomed in, and what do I see? So, there are 4 rows, right, 4x, 2y, and 3z, 2z. Okay. So, it is 4 into 2 is 8, 8 into 2 is 16. So, we have got 8 here and a depth of 2. So, the 16 threads. Okay. Each of this thing represents a thread. Okay. All right. So, of course, we can have 1024 threads in a block, maximum is 1024 in the new GPUs, and same thing kernel we define like this, but this dim grid will be a object which has 3 directions. So, it do not be just a number, it can be object which has 3 is a array, is a mini array in fact. So, to give an example, let us say we have an image of 64 by 55 pixel. Our images right now are much more dense, like 4K television, no? It has a huge number of pixels, but this for illustration. So, we divide into 16 by 14 blocks. There is a reason why I am doing it. So, 64 by 16 is what? 4. So, each block, so this block, in fact, these are 16 or 14, each this is a block. So, this block, if I look at this block, then it has threads. So, it has 4, so it is again organized in 2D. So, the 4 x component or x direction, and y direction how many? So, 55 I am going to write as 52 plus 3. So, 52 is 13 into 4 plus 3. So, there are 13 along x direction with 4 threads each. So, 13 of them except the last 13 of them have 4 threads in the y 4 dimension in the y direction, but the last one has only 3 threads in the y direction. So, this is not homogeneous, they need not be homogeneous. Of course, nobody says the grid should be power of 2. Okay. So, 13 blocks will be 4 by 4 threads, and last one is 16 to 13. So, this is x section 16. The last column, this whole column has only 4 into 3 threads, 12 threads. Okay. So, block this kind of arrangement is useful for 2D data or 3D data. Yeah. So, dim grid will be how will I say that? 16, 14, 1, right? This is going there, dim grid. How many blocks? And dim block will be 4 by 4 by 1 or 4 by 3 by 1. So, there are 2 possibilities, but you can make 4 by 4 by 1, you do not need to declare it, because I will run a kernel for simultaneously. I am not going to do this first, I mean till here, then do this, that will be waste of I mean that will be time consuming, right. That will do one operation, then second operation. So, you can launch it simultaneously. For the last one, you have to be careful. You should be accessing data which is there, not accessing data which is not there. Okay. So, that is why you need care, and organize your data as 2 to the power n. Okay, is best. Do not organize like 655. You are doing your simulation, it is in your control. Of course, if the data is given to you like in this format, then you can't do much, but if it is in your control, you should use as 2 to the power n. At least divide equally. So, this should, I would have liked it to be 52. So, divide it in such a way that threads are even in all the blocks. So, sometimes we need horizontal coordinates and vertical coordinates, and there are interesting, I mean it is quite obvious. So, vertical coordinate means in that direction, this y direction, no, vertical. This kind of syntax you will see quite often. So, block ID dot y, y means vertical direction. Okay. So, this y dot y, multiply this by block dimension dot y. Okay. So, block dimension was 4, okay, and let us say block ID is 3. So, it will be 0, 1, 2, 3. So, it is the fourth block in the vertical direction. So, that is 12 plus thread ID along y direction. So, let us say it is 2. So, 0, 1, 2. So, along y direction the coordinate will be 12 plus 2 will be 14. So, it is the 15th number in the y direction, 15th object in the y direction, that is what we will be accessing in the 2D grid, 2D data along y direction. Along x we have block id dot x, multi block dim dot x and thread id dot x. Now, please keep in mind that the id x is used even for y direction, you do not have id y dot y. Okay. So, this is a keyword, is an object which has component dot x dot y dot g. Okay. It's trivial if you see it, but keep this in mind. And block dim also is an object which has 3 components dot x dot y dot z. If I want to stretch in one dimension array, then what will I do? So, I get x coordinate and y coordinate, then I can get there. No, if I just wrap it around in column measure, then I can get the 1D index if I unwrap this whole array. So, you see it, you will meet it in your well, I mean you will see in some examples, but I will not do it here. So, the maximum values of blocks, how many blocks is allowed? Along x direction you get 2 to the power 31 minus 1, which is huge number. Okay. 2 to the power 31 is basically, how do I estimate this? 2 to the power 10 is 1000, 1024. So, qubit 3. So, that is 2 to the 30 is 1 billion, is 1024 into 1024 into 1024. So, this is 2 billion. So, along x direction you get 2 billion blocks. So, it allows, but of course, you do not use that big numbers. Along y direction is toward 15 minus 1, which is this number, and along z direction it is same. So, you can have lots of blocks, and block size, which will give the number of threads, is max at 1024. So, do not use the number of threads in a block more than 1024. Okay, XYZ is for 3D array or 3D picture. For 1D we use just X. Okay. Now, how is memory organized inside a GPU? So, this is from NVIDIA website. So, I think you should see this picture carefully. Okay. So, these are SMs. Actually, I forgot. Okay, these are SMs, SM1, SM0. So, I do not recall. A100 has something like 18 SMs. I do not remember, but there are SMs. And within SM there are registers. If you see it carefully, is 256 KB is a register, which is a big number, okay, kilobytes. And there is L1 cache and shared memory, L1 cache and SMEM, that is shared memory, which threads can, all of them can use, and that is 192 KB, that is our cache, L1 cache and shared memory. They can divide among themselves, or the system will divide, choose it appropriately. So, every SM has this amount of register and cache and shared memory. All this, so if your data is inside the SM, then it is fast. If your data is outside SM, then it is not, it will be slower. So, outside SM is L2 cache, and even, well, which is not so bad, but global memory, which is inside the GPU. Okay. Global memory, I do not mean the one in the host, is not the CPU memory. There is a CPU in the side sitting here, which has sent data to global memory. So, global memory is inside the GPU. Do not try to access the CPU memory or means host memory, that will be very slow. Mem copy, that is mem copy. Okay. This one does not require a copy. So, some data will flow on its own, you do not need to do much, do not need to do yourself. Data will flow from global memory to L2 cache and L2 cache to L1 cache, things will be done. These numbers are useful if you want to optimize your code. You should choose your threads and block in such a way that things are within the SM. I forgot how many blocks can be there in a SM. That is the number, I do not have it right now. How many blocks can you put, can you get in SM? Okay. So, CPU writes to global memory, as I said, this is the thing will be done. Then shared memory is fast, this memory is shared fast, shared by threads within SM. By the way, this shared memory is not accessible by threads here. The SM1 cannot access the shared memory of SM0. It has to go via global. So, it will like that. So, each thread can access a register and they will like to have their own register. Okay. So, now I think this slide you should have in your mind. Okay. This is different than CPU. Okay. Well, somewhat, but CPU, well, they have different cores, they are cache, but CPU will generate threads one after the other. Here threads are tons of them are there inside the SM itself. So, I think that is a key difference. We have thread huge numbers in SM, unlike CPU core which will generate one by one. So, it is like Rambo, no, you can deal with 1% at a time or 2% at a time, but these things can deal with thousands at a time.